So today we're going to talk about various types of chemical reactions, and I'm just going to have you make a list of those different types of chemical reactions, and you can write those all down. And again, this is nothing magical. This is nothing special. This is exactly what you've seen in the past in grade 10. And as I said a moment ago, this truly is exactly what you saw in grade 10 concerning the first three reactions: combustion, synthesis, decomposition. And then, as I said, tomorrow, single displacement with a little bit of new information. And then 5 is double displacement. Next day, Wednesday. Now, in that last lesson, some teachers have put the lesson on the collision theory at the beginning. And you know what? It's not a bad thing to do. That's where most teachers put it, but I just kind of got all mixed up one year, and I put it at the end, and it kind of worked out at the end. In that lesson on collision theory, we review how you know a chemical reaction takes place. And that's one of those things we're very good at kind of drilling into your mind, and because it's Monday, I'm not going to actually quiz you. But keep in mind, you've got all those things that let you know that a chemical reaction takes place, right? It involves the production of a new solid or a new gas, right? Energy is given off. It gets hot or it gets cold, or it produces light, right? What else is there? Now I'm stuck on these on Monday morning. What else have we got? Precipitate, new solid forms. Yep. What else was there? I really am. I've got Monday morning brain going just like you guys. New gas, new solid. We've got the energy absorbed or given off. Light is given off. That might be it. That might be those things. Yep. Color change, significant color change is a big one. Yep, that's right. That's the other one. It's the one I was stuck on. Keep those in mind as we go through all of these reactions, because that's what we use to characterize them. But again, very much review, and we'll be talking about that again on that last unit. Okay, so a combustion reaction. Typically, combustion reactions are rapid reactions. They happen very quickly. You can have substances reacting with oxygen in a slower fashion, right? The formation of rust when iron is oxidized in a slow fashion is also, substance reacting with oxygen. It does produce energy. It just produces it very slowly. And it does produce the oxide. So combustion reactions tend to be rapid. Two types of combustion reactions. Number one, you're going to have combustion of an element. And like I said, this should be 100% review from last year. Actually, when I teach the grade 10 course, I use this note pretty well straight up. I don't change a thing. I didn't teach grade 10 last year, so I didn't teach you guys, but if I had, you'd be rewriting the same note. you've seen this, right? This is what you talked about last year, correct? Yes? No? No? Do you remember last year? It was a blur? Yeah? Excellent. Good. I won't name names. This is going out on the internet later on today. So I'll spare you the embarrassment. Well, if last year was a blur for you, then maybe this is new. And I'll treat it like it's new. There are many elements that can undergo combustion, not just metals, but non-metals as well. Right, iron obviously can rust, can react with oxygen to form an oxide. But you can have obviously carbon burning to form an oxide, carbon dioxide. You can have hydrogen, you can burn hydrogen. You can burn any of these metals. You get them hot enough and put them in a nice atmosphere of oxygen, and they will burn, and they will literally burn. They'll react with the oxygen very energetically. How do you know if you've got a combustion of an element? You've got one thing, some element, plus oxygen gas to produce that element's oxide. All right? This is also an example of what other type of reaction. We're going to talk about it today. What is this also an example of? Yep. Yeah, it's a synthesis reaction because we've got two elements coming together to form one compound. So when two becomes one, that's a synthesis reaction as well, and we will write that down momentarily. There are some examples, and again, I have some demonstration or some little videos for those, and I will go back at the end of making my video here today and show you those videos. But for now, we'll just kind of roll through. Now you'll notice these are not necessarily balanced. I do that on purpose. Please take the time to balance them. I'll balance them for you here as well. Again, if you're writing in pen, that's fine. If you're balancing and you're a little unsure, grab a pencil, then you can fix it up if you feel you need to. Combustion of magnesium, I don't have a video for that. You've seen that. I'm assuming your grade 10 teacher took a little piece of magnesium and put it in a flame and made it burn really bright. Super bright? No? Yes, no? Nobody even responds here. I don't know. Yeah, supers. I hardly remember what happened on Friday, Mr. Sanders. Anyway. Maybe then on the demonstration day I will combust some magnesium for you. Normally, well, I could do that now, but I don't have any magnesium. I'll come back and balance that. Carbon, right? Carbon can come in many different forms. When you burn a piece of wood, it's primarily made up of carbon, so that's the reaction that's taking place there. Coal is primarily made up of carbon, so if you've got charcoal that you use maybe for a barbecue, that's primarily carbon. And so when you burn that up, you end up with carbon dioxide. Hydrogen can also be combusted. The term hydrogen, all right, was proposed by Lavoisier as the name for this particular gas, and that's because he knew that when you burnt this gas, it produced water, and that's what hydrogen stands for. Hydro being water, and gen comes from the same word as to generate or to make. So hydrogen means to produce water. So the name hydrogen itself literally comes from the fact that when you combust it, it produces water. All right? We will learn that oxygen, and oxy stands for sharp or acidic. It was also determined that when you burn various things in oxygen, you get acids. And we'll learn more about that when we talk about the acids and bases. That's where the word oxygen comes from. And here are a couple of videos. And if you go to the Google account, or you go to Google online, if you on a computer, not on your tablet, and you open up the PowerPlay, if you click on these, it'll bring you to the YouTube channel that has these. I'll show you that later on. But this is me burning some hydrogen, and this one has oxygen in it, and this one doesn't. But I'll describe that later on. We'll keep on going, and I'll show you those videos. I'll show you those videos when we get to the end. So again, I guess just for a statement for people who would be watching this video, that if you open it on a computer and it brings up the Google PowerPoint, the link will bring you, those links will bring you to those videos. suppose if you downloaded it and observed it on PowerPoint as well, the links would still be there. They'd be maintained, and they would bring you also to the videos. Okay, combustion of a hydrocarbon. Hydrocarbons are very important in our society in this day and age, in that many of our machines run on fuels that are hydrocarbon-based. Maybe your house is heated by burning of natural gas, again, a hydrocarbon. And, you know, barbecues, you may use a propane, again, which is a hydrocarbon. So hydrocarbons are chemicals that tend to be derived from crude oil, all right? And they turn out to contain hydrogen and carbon, and they burn really well. And because a hydrocarbon contains carbon and hydrogen, when you burn it, you get carbon dioxide, the oxide of carbon, and you get water, the oxide of hydrogen. And that's something I need you to know. All right, maybe in grade 10, every time you came across one of those and we wanted you to balance it, we gave you the products. But it's now the expectation that if I give you a hydrocarbon, like say CH4, and I say complete a balanced chemical reaction for the combustion of CH4, I expect you to know that you're going to add oxygen to it, and that it will produce carbon dioxide and water, and that you can balance it. All right? So it's now the expectation that you know how to get that balanced chemical equation. So let's look at some examples and let's balance them up. Yep. We're going to assume that we're dealing with complete combustion, and the answer is yes. Nothing else, just those two things. So here's a general formula, and this is technically complete combustion, all right? Maybe we could add that down. This is the general formula for complete combustion. COMB, good enough. If something undergoes incomplete combustion, it means that there's not enough oxygen to supply all those elements and turn them into their oxides. If you've got incomplete combustion, you get different oxides like carbon monoxide, very toxic gas. You also get soot or carbon, all right? We'll talk a little bit about incomplete combustion when I show you the demonstrations, but for here I just want you to, if I ask you, write the balanced chemical equation for the combustion reaction of, I want you to know that it will react with oxygen and it will produce carbon dioxide and water and then balance it up. Here I've put just example X and Y, where we can have various values of carbons and hydrogens in that particular reaction. Let's take a look at a few. Oh, I didn't balance those others up. Let's go back and balance those. That's terrible. I got so far ahead. Sorry about that. I got jumping here. Does somebody have this first one balanced? What do we got? Come on, this is easy stuff. What do you got, Liam? 2 and 2. I like it. How about the next one? Oh, the next one's a good one. Yeah. Sorry, balanced. Awesome. Good stuff. And how about the last one? What do I need to balance that one? Yep. 2 in front of the H2O. And 2 in front of the H2. You told me in the order in which you actually balanced it. That's awesome. It's perfect. Okay, very nice. So jumping back ahead, here I've got some examples here, and we'll balance these up as well. And I will always give you the formulas for the hydrocarbons. This first one is called methane. All right? Methane is produced in decaying matter by microbes. So there'd be methane produced like at a garbage dump. Like right now, you know, in Petrolia and in Watford, we're lucky to have 2 of the larger dumps in all of Ontario. Isn't that awesome? We're so lucky to have that here, so we can talk about it as an example. But I don't know if you've ever realized when you drive by the Petrolia dump there's a generator that's running all the time, and it's screaming as the motor runs and produces electricity. They're collecting the methane that's being produced by the garbage, and they're running an engine with it, and they're producing some electricity with it. That's kind of cool. They're not doing that at the Watford one quite yet. I can't remember why they're not. They didn't get a permit for the generator or something like that. Methane is also found in what we call natural gas. So if your house is heated by natural gas, and also our Bunsen burners run by natural gas, so that is methane, all right? And I will do a demonstration where I'll make some bubbles filled with methane, and we'll burn them and see what happens. We'll add various amounts of oxygen. We'll see what the oxygen does to the reaction. Let's balance this one up. Okay, so I'm going to go through this one with you just to review. Start with the carbons, 1, 1. Then do the hydrogens. 4, I need 2. Always half the number of waters that there are hydrogens. And now the oxygens, I've got 2 O's here and 2 O's there. That means I've got 4 O's. I need 2 O2s. All right? This second example is called acetylene. Acetylene is used in cutting torches. If you've ever taken a shop and you've used the cutting torch, that's a acetylene torch, an oxyacetylene torch. I'll generate a little bit of that and I'll burn that as well when I do my demonstrations. Nothing exciting here. Let's balance this up as well. Again, I'll go ahead 2, 2. Here, I only need 1 because I've got 2 H's, so I need 1 H2O. Normally I don't write the 1, but I know I'm going to do something here in a moment. How many O's have I got on the right? 3. So how many O2s do I need? What was my trick? 1.5, right? So 1.5, and that's unacceptable. So we're going to double everything. 2, 3, 4, 2. All right? Again, on a test, you can erase when you're doubling. You can do it now if you want. I'm just kind of illustrating the tactic that we use. Okay? Again, this is for complete combustion, when we've got lots of oxygen in order to supply those carbons and hydrogens so that they can burn completely. Okay. Again, let's not balance anymore. Don't write any more examples down. It's all the same thing now over and over again. This is propane, all right? And again, I got a couple of videos. These were done years ago. Yeah, this is me before I had a red lab coat. Anyway, and I'll show you those videos in a moment when we do that. But again, this one's already balanced, and this is propane, C3H8. And this is also a demonstration that I do. It's called the rocket car, where I put a little bit of ethanol. So this is ethanol here, and I did a balancing of ethanol for you. We have to watch about that extra O when we balance up the O's. That's the only thing you got to watch when balancing. Ethanol is a liquid hydrocarbon, and it is generated by fermentation of sugars, all right? Ethanol is the same alcohol that's found in beverage alcohol, all right? But there are various plants. I know there's one just outside of Chatham where they ferment massive amounts of corn in order to produce ethanol that then is supplied to the gasoline companies, and then they mix it in with their gasoline, and then you have an ethanol gasoline mixture. So it's very similar. Its properties are very similar to gasoline and can be burnt in most car engines. So it's an alternative fuel to using fossil fuels, all right? Again, I'll show you the video when we get to the end. All right, synthesis reactions. And like I said, I'm going to be on that demonstration day next week. We'll do the rocket car. I do it a little differently than that these days because I tried it. When I show you the video, I'll tell you all the exciting stuff that goes on when I burn things under very careful conditions. I don't burn things just for fun. It's for educational purposes. Synthesis reaction, chemical reaction in which two or more simple substances combine to form a complex substance. And again, if I'm teaching the grade 10s, you may have pointed this out. Okay, how do you recognize a synthesis reaction? From the general equation, when you're looking at a bunch of reactions and I ask you to tell me what type of reaction it is, how do you know it's a synthesis reaction? From the equation. Again, I guess it's evil. It's a Monday morning. You're all looking like a less than average grade 10s. That's too bad. Come on, let's be above average grade 11s. No, we're not going to strive for that. How do I know this is a synthesis reaction? Come on, Kira, bail me out here. And what's happening to them? Yes. So I have two things over here on the left, and I have one thing over here on the right. That's how I distinguish it. Two become one. Okay. All right. Might have to slow things down for you guys. Okay. Those little links there are links to different YouTube videos. Again, I'm going to show them to you. The aluminum and the bromine are not a video that I do. Bromine, and it's a liquid to start with, but it gets really hot and it produces some bromine gas, and it's pretty dangerous stuff. We have tubes of bromine gas that can be liquefied, but we should get rid of them. They're quite dangerous. Anyway, if it were to get out, the bromine gas. So this is not a video of mine. This zinc and sulfur one is a video of mine that I made a few years ago, and I did not, I don't have reactions for this one. They're not as exciting, but I do want to go through these. So, all right. The reason I haven't given you the products is because this is, again, the grade 11 thing that you've got to be able to do, right? Aluminum and bromine are going to come together to form a compound, and many students make the mistake of just squeezing it together and saying just AlBr2. But that's not how you determine the compound. Yes, we're making two things become one, but we still have to use our crossover method in order to determine the proper formula in which they come together with. So I have aluminum atoms coming together with bromine atoms. Aluminum has a charge of +3. Bromine has a charge of -1. So I'm going to cross them over as I would in order to get the proper formula. So if you can't generate the formula, you're in trouble, right? Which is what I've been saying. So we use the crossover method to get the official proper chemical formula for the product, and then we balance, all right? So you've got reactants, you find out the formula for the product, then you balance. What students want to do, because it's lazy, because you're lazy sometimes, you're all lazy, I said it. Anyway, and you want to keep it easy, you just squeeze it together, you say AlBr2, and it's balanced, it's awesome, it's great, I'm done, right? But no, that's not what aluminum bromide is. You got to cross it over in order to do that. So then we can balance, and we've got this 2-3 situation here, so I'm going to need 3 of those, and 2 of those, and 2 of those. All right? So the same thing's going to be true with zinc and sulfur. So I'm going to have zinc coming together with sulfur. And what's the charge on a zinc? Again, we should always have our periodic tables out. When we're doing chemistry, I told you a couple days back, keep that folder, keep that periodic table right in the front line of your, of your notes. Take it out, have the periodic table ready. Somebody track down, what's the charge for zinc? Yep, 2. And sulfur or sulfide, what's the charge for sulfide? Yep, 2, -2, right? So we got +2 and -2. We're going to cross them over. What do those numbers do? They cancel each other out. So that is zinc sulfide. So this is an example where we have that perfect match. Zinc wants to get rid of 2 electrons. Sulfur needs 2 electrons. They come together, we form zinc sulfide. This one is balanced, because sometimes it works out nicely. Copper and chlorine. Now, if you take a look at copper, you run into some trouble. Cu and Cl. What's the issue? Yep. 2 charges. There's 2 possible charges. And what I'm going to teach you here now is a very important skill. Whenever you're asking yourself the question of which charge to use, there's a little indication on the periodic table that tells you. Does anybody know? Did you read maybe in the little legend what the oxidation state? Just go take a look where the charges are. It might tell you. Does it tell you? What does it say? The most common oxidation state is bold. All right? And so what will happen is you'll actually get a mixture of the two, but you'll have more of the one that is the most common charge, the most common oxidation state. Which one is in bold for copper? Which one is the bolded one? Yep. Is it 2? Is it 2? So we will use the 2. Crossover 2. All right? Whenever you have the question of which charge to use. Now, if I gave you a compound and I told you it was copper 2 or copper 1, you stick with that charge because I tell you which one. But copper metal, any of these elements actually have no charge to begin with. They haven't given up their electrons yet. They've got all their valence electrons. Their charge is 0. Once they react with the chlorine and they start trading electrons around, then they develop a charge. The question again is, which charge will it develop? It develops the one in bold. That's what you're going to use to get the correct answer. All right? So whenever you start with an element of no charge and it becomes an ion with a charge and there are 2 possible charges, choose the one in bold. All right? Choose the one in bold. And then we can balance this up. Oh, I think that works out. That's another good one that works out, eh? And water and carbon dioxide. This is one where I wanted to give you an example of where 2 compounds come together. Now, this is tricky because we're not sure what the compound of the final thing is, and I'm going to tell you. This one is another example of where it comes together nicely. H3, or sorry, not H3, look at my addition there. H2CO3. And this is liquid, and this is a gas, and when it comes together, there's still lots of water around because what we're doing is we're forcing carbon dioxide gas into water, and when you mix that up, you get aqueous, whatever this is. And what is this chemical known as? You guys know the name to this. H2CO3. It's 2 H's with a CO3. What's the name of that stuff? It's got H's in the front, so it's an acid. And I'm going to, yep. It's carbon which? It started as carbon dioxide. Carbon hydroxide? Nope, there's no OH on that. Yep. Yeah, it's hydrogen carbonate. What's the classical name for hydrogen carbonate? Nope, it's not a bicarbonate. This is one where you might have to flip back. I'm going to make you do it. Carbonic acid, excellent. Carbonic acid. This is the chemical reaction that takes place when beverage manufacturers make carbonated beverages. So when you enjoy that pop for breakfast, because I see all you teenagers drinking pop in the morning. No, I haven't seen that in a while. You all go to Timmy's these days. Anyway, so when you have that pop for lunch, you're drinking a solution of carbonic acid. Carbon dioxide has been injected into that liquid, into the water. It's been agitated, and it reacts with the water to produce carbonic acid. You can even buy devices these days at I see them at Canadian Tire because I frequent Canadian Tire. It's the best store ever. Anyway, you can buy a device where you can make your own carbonated beverages, right? You put it in this container and you stick it under this machine, and there's a cylinder of carbon dioxide and it injects it into that, and you can make your own carbonated water, and you can put your own syrup in there. I don't know what you want to put in there. What would you like? Maybe make some Kool-Aid or something and turn it into a Kool-Aid carbonated pop or something. No, nobody drinks Kool-Aid. I don't know. Anyway, so that's how those machines work. They inject the carbon dioxide into the water, and that causes it to become carbonated, so that when you drink it down really fast, you drink it, and you can feel the burn in the back of your throat. That's because there's a little bit of acid in there. There's a little bit of carbonic acid, all right? You know, I always find kids that are that are keen in science, they'll come up to me and they'll say, did you know that you can dissolve a nail in Coca-Cola? Right? Have you ever heard that such a thing? You shouldn't drink that stuff, that all that type of stuff. And you can. You can actually get the metal to react with the acid. The key is you got to keep changing it out because it's a weak acid. This is a weak acid, not a strong acid. We'll learn about the difference of weak and strong acids when we talk about acids and bases. But it's a weak acid, so you got to keep swapping it out so that it maintains its strength in order to dissolve the nail. But you could do it, all right? By the way, it's a good thing it's a weak acid. We don't want to be ingesting a whole lot of strong acids. That would be pretty tough on your esophagus, I would think, and cause bad things to happen, all right? Anyway, that's how pop is manufactured. Yes? Yep, that's okay. Goodness gracious. She'll be fine. I'll talk to her in the next class. Okay, decomposition reaction. I'm almost done this note, and so when I get done, you might be able to make it. Let's wait till 9 and we'll see what happens. Then you can run down and run back. I assume you're going to the foyer. Yeah. We might even make it. Decomposition reaction, the last one that we're going to talk about. And then I'm going to show a bunch of the videos, and then I'm going to let you do some work. So decomposition reactions are essentially, well, they're essentially the opposite to synthesis reactions. We're not talking about decomposition in terms of like biological sense, you know what I mean? Like something dies in the forest and it decomposes, right? Again, the term decomposition means to break down. I guess that's the reference to the biological situation as well. Same thing here. So how do we know if we have a decomposition reaction and we're just looking at the reaction? What are you looking for in the reaction? From my voice, that's my condescending voice. That means I'm treating you like less than average grade 10s again. You should be offended, especially when I don't get a hand up here. How do I tell if it's a decomposition reaction? Yep. Yes. Starts with 1 and breaks down to 2. Very good. Maybe we're average grade 10. We're working our way up. Where'd you go? Okay. Again, just some examples. And you can see I've got some video associated with those. And like I said, I'm going to show that in a moment. Again, they're not balanced. Take the time to balance them, please. So the first one is a chemical called nitrogen triiodide. It's awesome. It is a very, very unstable chemical, and I know how to make it. So I'm going to show you some. Not today, in a week. But there's a cool YouTube video of a chemistry teacher who did a supersized version of it. I don't usually get quite that brave. And it is so unstable that if you have this substance and you touch it, it will explode. It is what we call a contact explosive. You just have to touch it and it will explode. And it breaks down into nitrogen gas and iodine gas. Let's balance this one up. What do I need to do to balance this guy? What's happening here? These are quick ones. Should be able to balance this just by, just going through it. Go ahead there, Joe. 3 here? No, over. Right. Nice. Okay. Number 2, this is hydrogen peroxide. Same stuff that you can buy in the grocery store, but the grocery store, if you buy peroxide there, or the drugstore, It's very weak. It's like 3%. The demonstration that is shown there is probably 30% hydrogen peroxide. We don't have any of that in the school. It's quite dangerous. But hydrogen peroxide will decompose and break down into oxygen and water. Sometimes hydrogen peroxide is used as a disinfectant. Let's say you get a cut. Sometimes people will put peroxide on that cut. It'll bubble away, and the bubbles are oxygen gas. And it is these free oxygen atoms that go around and break down the bacteria and things like that. Let's balance this one up. This one's a little trickier. We got a balance on this? Yeah, what do you got there, Eric?
2 on the water.
2 on the water? 2 on the hydrogen peroxide, because 1 O falls off of each one of these, right? And I need to have 2 of those O's put together to make the oxygen gas. Excellent. And I got a video for that. What is our H2CO3? What is that? Yep. It's carbonic acid. When you open your pop up, the decomposition reaction takes place, right? You have seen that place, right? You open it up and all these bubbles come out. H2O and CO2 gas. So this is an example of what we call a reversible reaction. If we jam a bunch of carbon dioxide into water, we turn it into carbonic acid, and you've got some nice pop. But if you give it a good shake and you open it up, you can force the carbon dioxide out, and the carbon dioxide leaves, and all the carbonic acid is turned back into carbon dioxide gas. All right? That's what happens when the pop goes flat. And flat pop is not very good. Or do some of us like flat pop? I've encountered students that like flat pop. Here we've got a flat pop lever right there. Leave that pop out, turn it flat. Is it sweet? Is it like it's disgustingly sweet? I find it's like, it's gross. No? To each their own. To each their own. The reason that it tastes almost sweeter when it goes flat is because acids tend to taste sour. So when you have pop that isn't flat, you've got the sweet from the sugar, and then you've got the sour from the acid, and it makes that awesome combination of sweet and sour. If you watch the Food Network, that's what the chefs always tell me. You've got to have the opposites in the right proportions. Anyway, so that's what makes the pop taste good. When the carbon dioxide leaves, it goes flat, and then you end up with just the sweet, and it doesn't taste so good. You can get this reaction to happen. This is my last reaction, by the way, Liam. If you want to go to that thing, you can go ahead, because then I'm just going to show the videos, and then it's going to be, so you can go and come back. Not a big deal. You're not missing much. Okay, so you can stimulate that reaction to take place in a couple of ways. Number one, you can shake up the pop. You can physically agitate it, right? Does anybody else know other ways in which you can get that carbon dioxide to come out, like really violently, which is what makes it exciting, right? You shake up the pop. That's what makes it funny. Yes? Add a Mentos. Yeah, Mentos is a classic one. I was going to find a Mentos video for you. There's like 3 billion Mentos videos on YouTube. And depending on, there was even one of a guy that had a Mentos suit on, covered in Mentos, and then jumped into a vat of Diet Coke. It was just the most bizarre thing ever. So you can find your own Mentos video for this when you have a chance, if you want to take a look at that. The neat thing about Mentos, when I was in university and we had to boil something, you would always add some calcium carbonate pieces to something that you wanted to boil. They were called boiling chips. And what calcium carbonate has is many little sharp surfaces, basically rocks. You're adding certain types of rocks to things that you wanted to boil. And what happens is all those sharp surfaces act as little spots or little starting points for boiling to take place. When you have something that is going to decompose into a gas, the same thing can happen. If you were to drop some calcium carbonate, even just some rocks into your pop, I don't know why you'd do that, but if you were to do that, you'd notice that it would start to bubble around the rocks, because there are certain little spots on the rocks that are nice and sharp, and that's where the gases kind of are attracted to in order to form lots of gas. If you've ever looked at a glass that has been old and used, maybe at a restaurant, and they order pop, there might be, say, scratches on the glass from going through a dishwasher or who knows what. You might notice that the bubbles form right on those scratches, on those lines. You can see a bunch of bubbles on them. Check that out next time. Let's say you're on a really boring date all right, and you really don't want to talk with the guy or girl, stare at the glass and take a look to see if there's bubbles forming on the side. And it'll be where it's kind of been kind of scraped. That's what the Mentos has. The Mentos has all these rough little surfaces on it that are perfect for the gases to accumulate in order to, form. And that's why it works so well. You put a couple of Mentos in there, and it really acts as these nucleation sites for the gas to form. There's one other way to get the gas to come out, other than shaking, adding something with lots of nucleation sites on it, like Mentos. There's another way. Any ideas? Don't try this at home, because I'll end up in trouble. But if you have a glass bottle of pop, and you take the lid off and you put it in the microwave, and you just run it for 30 seconds, you can get the carbon dioxide to come out pretty fast. But again, that goes like this all over the inside of the microwave, and then your parents go, "What are you doing? Why did you do that?" And you say, "Mr. Sanders told me to." Then I get into trouble. So don't try that one at home. But if you microwave pop, you will also drive out the carbon dioxide. The heat energy, again, causes the nucleation. Okay. So let's not write this stuff down. This is just a quick little kind of summary of what we've done. Identify the following reactions as combustion, synthesis, or decomposition. A, what is this? Yep. Synthesis. How did you know? Because it's making something? I'll take that. What was I looking for? Yeah. 2 and 1. 2 becomes 1. Excellent. You're right, though, both ways. What's this guy? What's B? Come on, average grade 10s. Yep, Abby. And why is that? Yeah, 1 becomes 2. Isn't this fun? Okay, C. What's this? I'm tricking you. But it's actually easier than you think. Pretty straightforward stuff. I'm going to pick on Kira again. What is it? Yeah, correct. 1 become 2. Many people look at that O2 and they want to write combustion, but it's a product. O2 as a product is not combustion. We need O2 as a reactant. D. What do we got? Joel, what do you want to say there?
I want to say combustion.
You're correct. Combustion. Combustion of a fuel. Oxygen is a reactant in that case. Complete. No, we're not going to do that. We're not doing that. There's some homework. As you're writing that down, I'm going to bring this particular video to an end.